Hello everyone, welcome back to another Youth Tutors video. Today we will be focusing on significant figures. This is an essential topic to understand whenever we're working with any kind of physics problems or equations. Now, if you're in high school, you're probably already familiar with this topic or maybe are learning it now. And some students in middle school are also dealing with significant figures. So that's kind of the targeted audience for this video. However, if you're still interested in just learning about significant figures, maybe for the future, stay tuned. So in order to know how to apply significant figures and count them accurately, we have to understand these 5 principles. The first one is that all non-zero digits are always significant. That basically means that, for example, 1 is a non-zero digit, 5 is a non-zero digit, 4 is a non-zero digit, and so on. So anything that is not a zero, we have to count. Next is interior zeros, or zeros between non-zero numbers, are significant. What that means is these right here are not between non-zero numbers. They're both 0, so we wouldn't count them. However, the 0 right here is between a 3 and a 5, and both of these numbers are non-zero. That means we would count it. Oh, and also we have this example right here. This 0 is between two non-zero, the 4 and the 2, so we count it. And it also happens with 2 zeros. It doesn't just have to be 1. Because both of these are between two non-zero digits, we count both. Okay. Oh, I went a little too far. There you go. Next one. Leading zeros, or zeros at the beginning of a number, are not significant. So in comparison to these interior zeros that are between two non-zero numbers, all of these are just in front of the number, and for this reason we do not count them. However, keep in mind, again, we see the pattern that we just learned in the second principle, or in the previous principle, and that is that while we don't count this one because it's a leading zero, because this one's between two non-zero numbers, we do count it. So always keep that in mind. Okay, we're almost done. The fourth one is that trailing zeros, or zeros at the end of the number, are only significant if there's a decimal point present, if they carry overbars. So if there's a decimal point and if there's overbars, trailing zeros or zeros at the end are significant. However, if none of these conditions are present, we cannot count a trailing zero. And we see that here. So this 0 is in between two non-zero numbers, so we count it. And this trailing 0 matters because of this decimal point. Same thing here. These 2 zeros go after a decimal point. That means we have to count them. This 0, however, does not have any kind of decimal points next to it. So in this case, if we had 10 point or 10 decimal, then the 0 would count. However, because in this number there's no decimals, even though, actually, this is something really important we have to understand. Even though we're always taught that 50, 100, 1,000, all these numbers have imaginary decimals at the end, we cannot count that, or we cannot apply that with sig figs. The numbers must clearly have a decimal at the end for us to count that 0. If it does not, we do not assume there's a decimal there. We just say that there's only one sig fig. And actually, this is a mistake because they're saying it's 2 sig figs. However, in order for it to be 2 sig figs, there needs to be that decimal. So I believe it was just a typo and they forgot to include the decimal. But yeah, it would only be true if that decimal point is present. And overbars just means this right here. Oh, actually, my bad. So they're saying 2 sig figs because of this bar right here. I completely missed it. I thought they were pointing to the top. So an overbar just indicates, it's kind of like that decimal. If you have 50 and then an overbar, that means that the 0, you do count it. However, if this overbar wasn't present, then we wouldn't count it. Okay. And again, like I said, if there's no decimal point, if there's no overbar, we do not count those zeros at the end. And then finally, exact numbers have unlimited number of significant figures. That means something like a measurement. For example, if you say that in 1 meter, there's 100 centimeters, unlimited number of sig figs, because it is a precise measurement. It's exact. You could also say there's 10 baskets in a room. That is an exact number. So you would say there's an unlimited number of sig figs. Even though 10 seems like there's only one sig fig, because you're saying 10 baskets, you're counting those baskets, it's exact. Okay, I hope this was clear. I'm just going to leave it here for a minute just so you can kind of skim it over. And now let's start applying. This is always the fun part because it can really give you a sense of how much you know and how many principles you really have to go over. So let's get started. The first number we have is 0.78910. So let's see the conditions. First, we have a leading zero in the front. We know leading zeros are never significant, regardless of whether there's a decimal or no decimal, so we wouldn't count this. Next, we have 7, which is a non-zero digit. We do count that. 8, another non-zero digit. We count it. 9, another non-zero digit. 1, a non-zero digit. Now, this is a trailing zero. However, we will count this trailing zero because of this decimal point present in our number. Therefore, after taking all these into account, we have 1, 2, 3, 4, 5. 5 significant figures. And you could just say sig figs to abbreviate. Let's do the next one. We have 853. As you can tell, all of these numbers are non-zero. Therefore, automatically, based on the first principle, we must count them. And for this reason, we say there's 3 sig figs. Now we have 1,000. As you can tell, this is a non-zero digit, so automatically it counts. These, however, are trailing zeros. Now, the only way a trailing zero could be significant is if there's overbar or a decimal point. Seeing that there's none of those present, we can only say there's 1 sig fig. Okay, next one. Same number, 1,000, but with a decimal point, which allows us to actually count the zeros. Again, this is a non-zero digit, and we have 3 trailing zeros. However, because that decimal point is present, we have to count them, which means now we actually have 4 sig figs. And this is a great comparison to show just how much of a difference a decimal point can make. We went from having 1 sig fig to 4 after counting those trailing zeros because of our decimal point. Okay, next one, 503.20. So here we actually have a few conditions, which I find really interesting. So first we have a non-zero digit, automatically counts. Then we have a 0, but it's between 2 non-zero digits. So we also have to count it because it's like an inner 0, I would say. Then we have a 2, which is automatically counted because it is a non-zero digit. And we have a trailing 0 right here. But the reason why we're counting it is because of our decimal point right there. So we have 1, 2, 3, 4, 5. 5 sig figs. We're going through these pretty quickly. Okay, next one. We have 83,012. Let's see. So 8 non-zero digits, 3 non-zero digits, a 0, but between, let's see. So this is an inner 0, and it's between 2 non-zero digits. So we count it. So 1 is a non-zero, 2 is a non-zero. So we have 1, 2, 3, 4, 5. 5 sig figs. Okay, next one. 2 chairs. Now remember the example I said. If I mentioned that there's 5 people in a room, 10 baskets in a room, 10 books in a room, those are countable numbers. I am counting that there's 2 chairs in a space. So for this reason, it is exact and thus has unlimited number of sig figs. Same thing as if I said there's 5,280 feet in a mile. There you go. In a mile, 5,280 feet. Or if I said there's 100 centimeters in a meter. Those are some examples of exact numbers that would have unlimited sig figs. Okay, now we have this one. So 0, it's a leading 0. It's in the front of a number. Now, please don't be confused by this. We do have a decimal point and zeros after and before the decimal. But remember, the decimal point only allows a 0 to count if it is a trailing 0, meaning a 0 behind a number. In this case, these are all leading zeros. So regardless of whether there's a decimal or overbar, we do not count them. If we had this instead, we would count these because they're behind the 7. However, that's not the case. So then we would just count the 7. We would say there's 1 sig fig. Okay, now I also wanted to include something with scientific notation in case you do come across that and become confused. When you have scientific notation, you can disregard this. You're only focusing on the number. So we apply the same rules. 3 is a non-zero, so we count it. 2 is non-zero, we count it. 9 is non-zero, we count. 1 is non-zero, and then 0 is a trailing 0, but because of our decimal point, we also count it. So we have 1, 2, 3, 4, 5. 5 sig figs. Finally, we have, let's see, whoa, this is a big number. It's 1,111,000. So let's see. 1 is a non-zero digit, so we count it. All of these are non-zero digits, we count, and these are trailing zeros, but because there's no decimal, no overbar, they are not significant, so we end up with 4 sig figs. And that is our final example. I'm just going to show them like this so we can get a better sense of it. I hope this concept became a lot more clear. Actually, there's some laws we didn't go over regarding multiplication, addition, subtraction, division that we will cover in our next video. So if you're interested in that, make sure to check it out. As always, make sure to leave in the comments any other kind of topic you would like us to go over, share this video, and subscribe for more tutoring lessons. Thank you so much and have a great day.